All of these circuits use a 9-volt power supply and a 250 ohm current limiting resistor in series with the LED. This voltage divider biasing circuit uses two 3K resistors to hold the base terminal at 4.5 volts. This puts it in saturation and turns the LED on. This is the same voltage divider biasing circuit, except now with a PNP transistor. Current flows from the emitter to the collector instead, so the LED had to be flipped around and then VCC and ground were swapped. This is the voltage divider circuit, again using an NPN transistor. The photoresistor is now replacing the bottom resistor in the voltage divider. Because of the selection of resistors from part 1, it does require a higher than ambient light to disable the LED, but once the resistance is decreased enough on the photoresistor, it will disable the LED. This is that same circuit with the photoresistor now replacing the top resistor in the voltage divider. This means that under bright conditions the light is on, and in dark conditions it will turn off. The transistor has been replaced with a PNP transistor. The photoresistor is connected to VCC. That means that in the original diagram it is taking the place of R2 in the voltage divider. That means that under bright conditions the LED turns off, and under darker conditions such as ambient light it turns on. This is the same circuit with the photoresistor now replacing R1 connected to ground. That means that in bright conditions it will be on, and in dark conditions the LED turns off. This is the NPN streetlight circuit generated by AI. It also generated a voltage divider circuit using the 2904 and still being supplied with 9 volts. The circuit is, or the LED is on under ambient light, but whenever it is extra bright you can see the LED turns off, so that would represent maybe broad daylight, and then at night the LED turns on. It generated a very similar circuit than we used before, just with different resistance values. Also, for the AI streetlight circuit, we can see that this circuit schematic really doesn't make sense. It suggests that the load is connected to ground as well as the emitter. If you assume that it meant that the load is connected to positive, then it does function. However, as it provided it, this circuit is non-functional. This is the delayed switching circuit, now using a 9-volt battery as a power source. The base voltage that turned on the LED at roughly max brightness was about 1 volt. The resistor in the RC circuit is 95K, so I calculated that the capacitance to turn on the LED was about 450 microfarad. We can see that about 5 volts, or 5 seconds from when it plugs in, the LED turns on. This is the delayed switching circuit using a PNP transistor. This requires that the capacitors start from a charged state, and then as they discharge, it will turn the LED back on. This is the AI-generated delayed switching circuit. It used a very similar design. It included a RB. It used a lot smaller resistor in the RC circuit, which meant the capacitors had to be far larger. It does still work to some degree. Turns on after about 5 or 6 seconds, except it does default to an on state, so you have to, the only way to turn the LED off involves it turning immediately back on. The schematic for this one is a little bit better than last time. Nothing is blatantly incorrect. It is still very difficult to follow, but constructed it did function as intended. I had to add an interrupt between the capacitor and the base in order to actually test the circuit, but it works otherwise. This is the push button switching circuit with a NPN transistor. This is the push button switching circuit with a PNP transistor. The button just shorts the base to the collector. This is the hand touch switching circuit with an NPN transistor. Whenever the collector and base are connected through skin, there's enough gain to turn on the LED. This is the hand touch switching circuit with a PNP transistor. Whenever the collector and the base are connected even through skin, there's enough gain to turn on the LED. This is the water switching circuit with an NPN transistor. Whenever they're connected through water, the LED turns on. They're not touching. I did not anticipate this one would work. I didn't think that there would be enough current flow through the water, even amplified by the current gain, to turn on the LED. This is the water switching circuit with a PNP transistor. You can see whenever the wires are connected through an amount of water, the LED turns on.